Welcome to this explainer. Today, we're stepping into the fascinating, high-stakes world of systems safety engineering. Think about the massive, incredibly complex infrastructures we rely on literally every single day, especially railway networks. Have you ever wondered how engineers systematically analyze these massive, complex hazards to prevent catastrophic failures before they even happen? Well, I can tell you it's definitely not just guesswork. It's a highly structured, rigorous science. So let's dive right in and look at the architectural framework that keeps these systems running safely. We've got a really great lineup for today. We'll be covering the Hazard Analysis Toolkit, bottom-up FMEA, top-down FTA, mitigating overruns with ORAM, and finally, the layout risk method. All right, let's kick things off with Section 1, the Hazard Analysis Toolkit. So the central question of systems safety engineering is really this. Once a potential disaster or hazard is spotted, what exactly do we do next? As we just established, we don't guess. We apply hazard analysis. This is the methodical process of evaluating identified hazards to genuinely understand their underlying causes and their potential real-world consequences. Think of this as mapping the entire anatomy of an accident before it ever actually has the chance to happen. We want to know exactly what triggers it, how it propagates through a system, and what the ultimate end result looks like. And this brings us to a really brilliant dichotomy between our first two foundational techniques. Engineers essentially approach the exact same problem from two completely opposite directions. On one hand, we have FMEA, which is a bottom-up approach. It starts at the absolute smallest component failure and asks, okay, what happens next? On the other hand, we have FTA, which is a top-down approach. It starts with the absolute worst-case scenario, the disaster event itself, and works backwards, asking, how on earth did we get here? Moving right along to Section 2, bottom-up analysis using FMEA. So, FMEA stands for Failure, Modes, and Effects Analysis. Sometimes you'll see it extended to FMECA, which just adds a criticality element to the end. The absolute crucial point to remember here is that this technique starts at the ground floor with the smallest cogs in the machine. We look at an individual component, figure out literally every possible way it could break, why it would break, and then we trace the ripple effect of that single isolated failure all the way up through the entire system. Now, what's really fascinating is how this is applied in the real world on a railway track. Imagine a specific hardware component in a track circuit, say a trackside relay box, or the insulated block joints that separate rail sections. FMEA isolates that one tiny part and asks a very specific question. If this relay fails to open when a train shorts the circuit, what exactly happens? Does the signal stay green when it should turn red? Because if it does, that's a false clear. That is a catastrophic bottom-up failure that FMEA is specifically designed to catch and engineer out. The whole workflow operates like a methodical chain reaction. Step 1, identify the component's failure mode. Basically, how does it break? Step 2, determine the root cause. Why exactly did it break? Was it vibration, flooded ballast? Step 3, analyze the system effect. Does the entire network go down or just one single signal? And finally, Step 4, assess the criticality and redesign. We use this direct structural analysis to inform safety design changes, like adding necessary redundancies so the system fails safe. Let's pivot to Section 3, top-down analysis using FTA. Here, we move from the micro-level component specialist to the macro-level generalist. FTA, or fault tree analysis, is a top-down deductive technique. What makes this so incredibly interesting is that we aren't looking at individual parts anymore. We are looking at a full-blown event. We put the undesirable top event, say a head-on collision between two trains, at the very top of our whiteboard. Then we deduce downwards, mapping out the precise combinations of causal factors, both human and technical, that would have to align perfectly for that disaster to actually happen. The process builds a literal tree structure, very much like a detective deducing a complex sequence of events. First, you define that top event. Second, you deduce the contributing branches. Maybe it was a brake failure combined with a signaler error. Third, because we map this out with logical and and OR gates, engineers can actually calculate the mathematical probability of this specific disaster occurring based on the failure rates of the branches below. Finally, Step 4, we implement protection measures to sever those branches and prevent that fatal combination of faults. Okay, so we have our foundational engineering tools, FMEA and FTA. They are fantastic. But how do we apply this logic when things get incredibly specific? I want to pose a question to you.
How do we systematically analyze the specialized operational risk of a train simply running a red signal? Well, to answer that, we first need to define the exact operational threat we're talking about. In the railway industry, this is known as a SPAD, which stands for Signal Passed at Danger. It's exactly what it sounds like, an event where a train overruns its authority at a specific red signal. This is without a doubt one of the most critical hazards in any railway network, and general tools sometimes just aren't enough to capture the nuanced physical realities of the track. Which brings us to Section 4, Mitigating Overruns with ORAM. Because SPADs are such a specific, dangerous threat, engineers use a specialized analysis called ORAM, or Overrun Risk and Mitigation, and it brilliantly separates the risk into two distinct elements. First, it looks at the likelihood of a SPAD occurring, meaning what are the actual chances a driver makes a mistake or the brakes slip at this specific signal. Second, it looks at the probable consequences, meaning once that mistake is made and the train actually slips past the red light, what happens next? Does it safely slide into an empty stretch of track, or does it merge directly into oncoming high-speed traffic? ORAM essentially operates on a tiered priority system. Step 1 is absolutely always trying to reduce the likelihood. We might improve the visibility or sighting of the signal, so the driver literally can't miss it. But if we can't completely guarantee a train won't run that red light, we move to Step 2, reduce the consequences. We actually go in and alter the track layout. We might set points beyond the signal to divert the overrunning train onto an empty, safe path. This is a concept known as flank protection, and it allows the infrastructure itself to safely absorb the human error. And finally, Section 5, the Layout Risk Method, or LRM. All right, now we are scaling things way up. We're moving from a single signal to entire massive railway junctions. LRM is an incredibly powerful quantitative technique used to compare the absolute risks of completely different track layout configurations. This is a comparative tool used at the absolute highest levels of planning. When engineers are staring at a blank map and deciding between two different multi-million-dollar infrastructure designs for a new junction, they use LRM to determine, mathematically, which design is fundamentally safer. As you can probably imagine, the data required to do this is just intense. It is extremely labor-heavy. LRM requires engineers to identify every single signaled route in the design. Then, they classify potential conflicts. Are they head-on, converging, or crossing conflicts? They actually calculate time windows, figuring out the exact number of seconds a train in a conflict zone could be hit by another train experiencing a SPAD. And they have to calibrate the probability of that SPAD occurring based on the specific, unique location of every single signal in the junction. But it doesn't stop at just the track geometry. LRM gets deeply mathematical regarding the human cost, too. It factors in variables like potential impact speeds based on local track limits. It looks at the physical crashworthiness of the specific rolling stock that'll be used on that line. It even factors in passenger loadings. I mean, how full is the train likely to be during a Tuesday rush hour versus midnight on a Sunday? By aggregating all of this, LRM reveals the true, holistic potential severity of a layout failure. Which really leaves us with this final, powerful thought to consider. By combining bottom-up logic that examines the smallest trackside relays with top-down deduction analyzing catastrophic top events, and then layering on highly specialized tools like ORAM and LRM, we have to ask, how exactly do these analysis tools weave an invisible safety net across the complex infrastructures we rely on every day? It is genuinely a marvel of modern engineering. Every safe journey you take is built on this hidden foundation of rigorous hazard analysis. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.